All right, we're going to try this today. We'll see if you like this better than writing on the board. So I'm going to try to write on my new tablet PC. It's going to be projected on the screen. So give me feedback as to whether you like this or not. So this should be on Zoom. You guys are all seeing it, right? And better already, no glare from the lights, and it's in focus. Gosh. All right, so first off, you guys have a flight test assignment you're working on, right? I had a couple questions. I forwarded one to Biology. They were asking about trying to get up to 120 knots indicated. It may be that he just says fly as fast as you can. You're going to shoot him an email and ask the question?
Yeah, I will.
You did? Okay. Any other issues? We have an exam next week, Thursday, right? 30-minute exam in class. So the exam will take 30 minutes, and then we'll do lectures and normal class stuff after that. Make sure you bring your book. You may or may not need it, but you will, on various exams during the semester, need your book. Typically, I give some closed book part of the exam and then an open book part. I'm not sure what I'm going to do within the 30 minutes just right now, but you will need a copy of the book, and that means if you have an electronic copy, you'll need to print out the chapters that we've covered and bring it with you. Does that make sense? I see you guys looking at me strangely. The chapters we've covered. Up through longitudinal forces and moments. I don't know the sections, but it's on the syllabus. Just go down to where it says longitudinal forces and moments, and that's the section. How many of you guys have electronic books? A couple. You're not going to have to print out the whole book because we don't cover the whole book, just the sections that we cover. And I typically will give you a heads up if you need something from the appendix. One of the airplanes, I'll let you know which one you need because you don't need to copy the whole thing. All right, anything else we need to talk about? So I already started the notes for this class because I wanted to get familiar with OneNote to make sure I was going to be able to make it work. Trying to lower the lights partway, but not completely. Is it okay on the screen the way it is with the lights? Yes? We're good? Okay. I thought we could dim the lights in here halfway, but I don't seem to be able to get it to stop. It's all or nothing. All right, so today we're going to talk about airplane side force. So we're talking CY Q bar S, and we have our traditional linear model in terms of beta, aileron, and rudder, and there's ones on those because we're still talking steady state forces and moments. So this is the model we go with. Again, if we add extra stuff to the airplane, we'd add another term for that. And so the first one we're going to talk about is CY beta. And we're going to do the component buildup method just like normal. Where the wing effect, the fuselage effect, and the vertical tail effect. And for the wing and the fuselage, we'll talk through those. And for the vertical tail, we'll actually derive the value. And it's not hard. It's the side force due to beta, so we'll figure out the angle of attack, multiply by the lift curve slope, Q bar S, and we're good. So same procedure as before. Remember that a positive beta gives a velocity coming in from the right side, or the airplane is moving to the right. They both have the same effect. It depends on whether you're an observer on the airplane or out stationary. All right, so part of the deal is I'm going to scroll up to write more. So if I scroll up too fast, somebody starts shouting and say, stop, wait, please, hold on, all right? All right, so the wing effect is mainly dihedral. So if you look at the airplane like this, and we're looking at the aft, so this is an aft view. So that means the relative wind, part of it is coming in from the side, right? I guess you guys get to see my email popping up here as well. So just like in the rolling moment, the wind coming in from the side is going to push on the airplane. And instead of rolling the airplane, we're looking at side force now. So it's going to push on the wings, and we're going to get a negative side force. And if you look at the fuselage, we're going to get an effect from there as well, right? So the wing effect is mainly dihedral, and the fuselage effect is going to depend upon the size and shape of the fuselage. So we can't really come up with formulas, but if on a homework or a quiz I ask you to explain the side force due to beta of the fuselage, you'd draw this picture. Because the wind coming in and hitting the fuselage is obviously going to push it to the left. And the wind coming in is going to give, is going to push on the wing here, and it's going to push on the wing here, and push the airplane to the left. So the key feature here is a positive beta produces a negative side force, or side force coefficient. All right, how about the vertical tail? Draw it better in there. Obviously, the relative wind is going to push on the side of the tail as well. And we can calculate that because we can look at the forward velocity and the side velocity, calculate an angle, beta, and then multiply by the angle of attack. Well, that's the angle of attack, multiply by the lift curve slope. So the next thing we're going to do is deliberately derive that. So far, so good? All right, so to build up the force, we're going to take the lift curve slope of the vertical tail, and we're going to multiply it by the angle of attack of the vertical tail. And we already did this last time. It's going to be beta minus the side wash. And for the side wash, we're going to use the model where the side wash changes with beta. So 0 beta, we get no side wash because the airplane's symmetrical, right? All right, so there's the angle of attack. You can call this alpha of the vertical tail if you want. So it's CL alpha V times the angle of attack with the side wash model. And then, of course, we have to multiply by the dynamic pressure and the area. And this gives us a aerodynamic side force in the y direction. And it's negative, correct? Because the positive beta gives a negative side force. And as always, we want to turn this into a coefficient. So we divide by due to beta. Oh, vertical tail, yeah. And here we're just looking at the beta effect. So we really ought to subscript beta, but that gets kind of crazy. So this is the vertical tail effect. And then we're going to convert it to a coefficient. So we're going to divide by, so keep this separate here. We're going to divide by Q bar S. And then we get the normal ratio of the dynamic pressures. And we get the normal ratio of areas. And that gives us Cy beta of the vertical tail. So that's just, you pull beta out from here, and you pull beta out from here, and then we collect everything that multiplies beta, and that's what we call Cy subscript beta. You can also think of it as taking the derivative of that. So this is Cy. You can think of it as taking the derivative with respect to beta, because if it's a linear model, then if you take the derivative with respect to beta, you get that term Cy beta V. So this is a nice, neat formula. Now I need to reach the other side. Let's see how this can work. All right, I'm going to have to just write in here. This is supposed to be d sigma by d beta. And then it's a to v sv over s. So there's a formula for the vertical tail, and then for the fuselage and the wing, it's just a picture and an explanation. All right, notice from this as well, a positive beta gives a negative side force. So now we're going to ask the question that we always ask. Do we like that? Do we not like it? Doesn't matter. Yeah, and I know the easiest one is to say it doesn't matter, right? Well, what do you think? Here we've got an airplane. And the airplane, to create a side slip, is going to move sideways like that. Right, the airplane is moving to the right. Or a gust comes in from the right. So if we want to get rid of that disturbance, we want a force in the opposite direction. So if the gust is coming in, we want the airplane to be blown to the left because that gets rid of the side slip. So this is actually good. And that's, we're starting to talk about what's the stability criteria, which we've talked about in 514 as well. So a lot of this is reviews. A lot of it will be going into more depth. And we're taking it faster in here than we did in 514 to get everybody up to speed. All right, so the other one, the next one, is Cy delta A. That's the side force due to aileron. So we're talking about one aileron being deflected up on one wing and down on the other wing. In Roskin, he said this is pretty small. You get a little bit from that flap being up or down, but not significant, so we can usually neglect this. And then the last one is the rudder. So if we look at, again, our view of the airplane, and we have a rudder deflected. That's a crappy picture. Let me see if I can do better. Let me draw it from the top. So there's our rudder, positive rudder deflection. It's obviously going to generate a side force like that because we have a change in camber of the vertical tail. And we can calculate that just like we can everything else. We take the lift curve slope of the vertical tail and then the angle of attack effectiveness of the rudder times the rudder. So this gives us the effective increase in angle of attack that you get from that camber due to the rudder. And then we multiply by the area and the dynamic pressure, and we get the total force. Notice this is positive just by definition of what positive rudder is. So positive rudder produces positive side force. And so the effect of the rudder is everything except for the rudder term. So if you talk about Cy delta R, you get CL alpha V, the rudder effectiveness, don't need the rudder. And then we turned it into a coefficient by dividing by Q bar and S. And so we get, all these formulas look a lot alike. They always have that A to V and the SV over S. So now we've completed the side force. We have the side force due to beta, comes from the wing dihedral, the fuselage, the vertical tail, and the rudder. No ailerons, really. So questions about that? So the book talks about how there's some other minor effects. And one of those is what he calls differential stabilator deflection can generate a side force. So what's happening is, notice that this stabilator over here is right here is tilted up, and this one is tilted down over here. So you get more lift on one side, so you get more air pressure, less air pressure, and so that differential in air pressure can cause a side force. So if we had this effect, then we'd have to add another term onto our linear model that would include this effect. I'm just mentioning it here. Again, anything that you add to the airplane that could generate a side force, like a bomb or a missile or a space shuttle on top of your airplane, you have to add the effect for that as well. All right, so now we want to talk about the last one. And this is yawing moment. So Cn, of course, is non-dimensionalized yawing moment with respect to Q bar, S, and B. And then we want our linear model again. And it's going to look just like the rolling moment and the side force because it's all the same variables. And so we want to spend a little bit of time talking about each one of these because this is an important stability effect. So we'll ask the question, is this good, bad, or we don't care? This is the intended effect of the rudder. The rudder is there to yaw the airplane. And then this is a side effect. Seems like in life, no matter what you do, there's the intended effect and the side effect, right? Happens in airplanes. I was talking to my neighbor who's a pathologist, he's a doctor, and I was talking about medication and stuff, and he goes, I said, well, this medication has no side effect, and he said, oh, everything has a side effect. It's just whether it's significant or not. So in this case, the rudder is there to yaw the airplane, but the ailerons can produce a yawing moment, and we're going to talk about that as well. Now remember when we talked about rolling moment due to rudder, we got a side effect. The rudder is not intended to control roll, but if we needed to, we could use that as a redundant flight control to roll the airplane. So in that case, it's maybe a good side effect that we can take advantage of. All right, same deal. We're going to talk about C and beta. And it's going to be due to the wing, due to the fuselage, and the vertical tail. And I'm going to show you a drawing of something that happened to a senior design team where they got this effect and they didn't count on it. Roscom says this is small at low angles of attack. So again, this is a wing effect due to side slip and yaw. And if you think about it, the wing is pretty much close to the CG. All right, so if we drew a top view, here's the wing. CG is usually like right here. And so if we have some side slip, if you do get any generated side force on part of the wing, it's going to be pretty much symmetrical about the CG, and you're not going to get much of a yawing moment just because there's not much moment arm of the force. All right, so the wing is small. This depends on, just like the side force, the fuselage shape. And that's where I'm going to draw you a picture of an airplane that one of the senior design teams built. So can I scroll up? Are you guys caught up? All right, so a while back, the senior design challenge was to build an airplane that carried, I believe it was softballs. Might have been tennis balls, but so these were big balls, and they had to carry as many as they could in a fuselage. And so one team designed an airplane. This is a side view. with this big fuselage so that they could put a lot of balls in here. And I'm not throwing the wing on here, but this is the fuselage. And so the way this thing was set up was that the CG turned out to be somewhere like here. And the vertical tail is going to produce a yaw in a side slip to yaw the airplane back into the side slip, right? We want the yawing moment generated about the CG to be like this, positive yawing moment, because if you get a side slip coming in like this way, if you yaw that direction, you eliminate the side slip, right? Okay, so the vertical tail will do that, but what about the fuselage here? What's that going to do to this relative wind, the beta? Do you see what happened? It's going to push on that huge area up here, and it's actually going to yaw the airplane in the wrong direction. So they loaded up their airplane, set it on the runway, actually the parking lot, and the guy flying it started to go down the runway, and once they got a certain amount of airspeed up, the airplane flipped around. Because then it was stable with this part going, essentially going backward. So with the air coming in backward on this, then this part of the fuselage actually kept it stable going backward. And they didn't have a big enough vertical tail to counteract that. So what's your senior design challenge this year? Do you have it yet? Carry what? Pennies? Oh, so that's a small payload, but it's heavy, right? Are you supposed to drop them? No? Otherwise, I'd be down there. No, I'm kidding. That's interesting because there's a coin shortage, right? You know about that? Like pretty much most stores you go into, they say they're not going to give you change back for two reasons. One, if they give you change back, it could have all kinds of viruses and germs on it. And the other is that there's a shortage because people aren't bringing their change into the bank. So I collected all the change off my dresser and took it to the bank 3 months ago and got $14. Yeah. They're what?
It's an indoor.
Oh, it's indoor?
Yeah.
So where are you flying?
Basketball court.
Coke Arena?
He didn't say anything about a particular location, but he was like it would be a basketball-sized game.
Yeah, okay, that's cool. So it's a smaller plane?
Well, the battery limit for only 200 milliamps.
So it's going to be smaller, I guess, and you have to carry as many pennies as you can. Does carrying a dime count for 10 pennies? I don't know.
Like dollar bills over.
Yeah, a dollar bill would be even lighter. I'm guessing it's actual pennies, right? Okay. So the last thing we want to look at for CN beta is the vertical tail effect. And so draw a picture like this. So we're talking CN beta vertical tail. Here's your CG. Here's the vertical tail, made really big. Let's put a rudder on it because we'll eventually need it. Hey, I got a little more page over there. All right. So that's positive rudder, and there's the vertical tail, and here's our positive side slip. And again, you're going to see this derivation looks exactly the same. Here's the aerodynamic center. We're going to get a side force due to the vertical tail, due to beta. And now the only difference between the rolling moment and the side force is now we have an X distance back to the vertical tail, and that's going to be our yawing moment arm. Before, for the rolling, we had the ZVS. That's the vertical distance. So it's going to be the same force we had before. The only thing that changes is the moment arm. So same buildup. We have CL alpha V. That's the lift curve slope of that flying surface. That's the vertical tail. The angle of attack of the vertical tail is beta. And the sidewash model. And then we have Q bar V, SV, and then we have to mark, put an S on this because it's in stability axis, times the moment arm. So here's our force, and here's the moment arm. So that looks a lot more complicated than just normal statics, right? Statics, you have F times X. So what makes this more complicated is that this is an aerodynamic force. So it's the aerodynamics that generate the force that make our formulas more complicated. But we're all aerospace engineers, so we're used to that, the forces. So let's see, did I get everything? CL alpha times the angle of attack, Q bar S V, XVS. And so this gives us the side force. Oh, sorry, the moment arm, the yawing moment. Make that an N. I need to learn how to erase on this. Anybody know? Anybody use OneNote all the time? I was hoping I could push this button on and it'll erase, but no. So that's the yawing moment, and then of course, to turn it into a coefficient, we divide by Q bar SB, and that gives us Cn beta the vertical tail, which is everything except for beta, because we factor beta out, and then the stuff that multiplies beta is Cn beta V. What sign? Did I get the sign correct on there? There's positive beta. We get a force in this direction. It yaws in that direction, right? Is that positive or negative? By now we know it's positive. If you have to check, put your thumb down the z-axis. Nose right is positive yaw. So the correct sign here notice in all those formulas, because we non-dimensionalize, we get a non-dimensional distance. Just like in the longitudinal stuff, we had xcg bar, which was xcg divided by c bar. Here we get divided by b because it's lateral directional forces and moments. All right, we've already talked through this, but now notice that a positive beta produces a positive yaw, and that is good because it yaws into the side slip, which means it reduces the disturbance, beta. So after we're done with the forces and moments, we're going to actually list all of the stability parameters and derivatives like these. Remember, CL beta was negative because we want to roll away from the side slip. Side slip in an airplane is generated by the airplane banking and then starting to fall to the right. And so rolling back upright gets us that stability. The side force causes the airplane to slide away from the side slip, and then the yawing moment yaws into the side slip, which reduces the angle. Cm alpha, you can think about the same way. If you get an alpha gust, the airplane pitches down into the additional angle of attack to reduce it back. All right, so the next thing we're going to look at, we got the control derivatives. We have Cn delta A and Cn delta R. And in the aileron effect, we're going to look at two effects. Oh, sorry, we're going to look at an aileron effect. And then we talked about roll spoilers. So we're going to look at that effect as well. And there's a couple nice pictures in your textbook, so I'm going to switch the screen sharing over to that. All right, so this is the aileron effect. So this is positive. Oh, what the heck's that? Big pen. Hang on. All right, I may not be able to write on this. We'll just point to it. So this is, with positive aileron, this aileron is deflected up over here, and this deflection, this aileron on the left, is deflected down. So right side up, left side down, we get less lift on this side and more lift on this side, and that's what gives us a positive rolling moment. We get less drag over here because we have less lift, and we get more drag over here. So what that means is, in addition to the rolling moment of the lift differential, we get less drag here and more drag here, and that gives us a negative yawing moment, which is what they're saying right here. So that drag difference, less on the right, more on the left, gives you a negative yaw. Okay, so hold that thought. The ailerons are going to give a negative yawing moment for a positive roll. How about spoilers? So here's a spoiler, a lift spoiler. On this side, it's deflected. On this side, it's deflected up enough to spoil the flow. In other words, you get stall behind, and that's what they're showing you right here. So it's stalled, which means the lift goes down and the drag goes down. Sorry, the lift goes down, the drag goes up. So here's the decreased lift, here's the increased drag. And so that means you actually get a positive yaw with a spoiler deflection, which is the opposite of what we got from the ailerons. So now we have to decide, is that good or bad, or do we care? So you guys get the two explanations? with the ailerons, less drag on the right, more drag on the left, you get a negative yaw. With the spoilers, you get the opposite effect. You get more drag on the right because of the separated flow. All right, so let's write that down. So the aileron effect is Cn delta A is negative. And for the roll spoilers, Cn delta A is positive. Okay, so now imagine an airplane going into a turn. You do a positive aileron deflection to start a turn to turn to the right. And I forgot my foam airplane. I meant to throw it in, so we'll use my backpack. So here's our wing. We're going to bank this way to turn to the right. Which way are the ailerons yawing us? They're yawing us the opposite way. You're yawing out of the turn. And so that's considered to be bad. Pilots don't like that because they're trying to turn to the right, and yet the nose goes to the left. So this is what's called adverse yaw. And whereas with roll spoilers, you get a yaw to the right, and while you're banking to the right to turn to the right. So you could call this proverse. Although I didn't necessarily like that word. So I looked up antonyms to adverse, and I got advantageous. So maybe that's what we ought to use, is advantageous yaw. Assisting, good, helpful, kind, lucky, nice. Auspicious, beneficial, friendly, favorable. My son's in Scouts. If you were in Boy Scouts, it sounds like the Boy Scout law, right? Trustworthy, loyal, helpful, friendly, courteous, kind, obedient, cheerful, thrifty, brave, clean, and reverent. So that's why on a commercial airplane, you see ailerons and roll spoilers. The ailerons give good roll control with not much additional drag because they don't spoil the flow. But then when you're going slow, the roll spoilers come in and help give a lot more bank angle authority. And when you're going slow and you're doing a lot of turns to try to land or take off, then you can cancel out the adverse yaw from the ailerons with the proverse yaw from the spoilers, and you can schedule it so that you get good behavior of the aircraft when the pilot's trying to control it. So you'll see both of those. And again, I told you, sit where you can look out the window and you can see both of these deflecting on an airplane whenever we all decide to start flying again. All right, so then the last one we need to do is this one, Cn delta R. And that's the yaw due to the rudder. And that's where we can even go back up here and look at our picture from before. And that's why I drew a rudder, is if you see this rudder deflection that we had from before, we talked about side force due to rudder is like that, right? So which way is that going to yaw the airplane? It's going to give us a negative yaw. So the formula for the yawing moment due to rudder is going to be that force from the rudder times XVS, which is our moment arm. And so again, like I keep saying, it's just we're going to fill in here whatever the force is being generated, then you multiply by QS and then the moment arm. So that formula is going to look real familiar. It's CL alpha V again, because that's how we predict the force. The rudder effectiveness. And then we get QV, SV, and then XVS. And it's negative because positive rudder gives negative yaw. And we do the normal thing where we divide by Q bar SB, and then we get the coefficient. Everything that multiplies the rudder, we collect together, and that's what we call CN delta R. So key feature here is positive rudder produces negative yaw. And do you remember which way it rolled the airplane? Positive rudder, which way does it roll? Go back to our picture. I'll go back down so you can finish writing. From this, the AC is stuck above the center line, right? And so this force is going to roll the airplane in a positive manner. So that's where we could get roll control as well, if we want it. Now we have to be careful because you deflect the rudder and it's going to yaw and roll, and the yaw will generate a side slip. And so we have to figure out, well, if we get side slip from the rudder, how does that roll the airplane as well? And so we'll have to add the two effects together. So fundamentally, the rudder produces negative rolling moment and a negative yawing moment and a positive rolling moment. And we have to ask the question, good, bad, don't care. Is the negative yawing moment from the rudder a good thing or a bad thing? Look back in your notes. What did I say way back when we wrote the linear model? What is CN delta R? That's the intended effect, right? So the sign of this is not really good or bad, is that we get that yaw because we define positive rudder to be the way that it is. So it's, I wouldn't say it's good, bad, or don't care. It's what we intended. And we talked about this, but why not revisit it? How about the lift or the roll? We can make this a script L. So is the negative rolling moment, sorry, the positive rolling moment from the rudder, good, bad, don't care, intended, unintended, side effect? It's a side effect, right? But we can take advantage of that. All right. So the next thing we're going to talk about is the forces and moments due to the thrust. Lateral, directional. It's going to be easy, but let's take a short break for a message from your sponsors. No, I'm kidding. So feedback. What do you like this? You'd rather I write on the board? Good, bad, don't care. It's a side effect. Works either way. What do you think? How many people like this? How many people like the board? Okay, so a couple people. So maybe we can switch back and forth. Yeah, I'm not sure which I like. If I'm up and moving around, it kind of keeps me awake. I don't know if it keeps you awake. A little bit. If I'm sitting here while I'm lecturing, I'm going to have to spend more time at the gym to stay in shape because I'm not getting the activity. All right, let's take a break, go get a drink of water, and we'll finish this up. All right, I have to ask what might be an embarrassing question. I realized I went to the bathroom and I just had the microphone on. Did that come through on Zoom? Nobody knows? Okay, good. I mean, all you'd hear is the toilet flushing. I hope. I didn't even thought of that till I was walking out of there. I need to leave my microphone here. All right, let's see, what's next? All right, so now we're talking about steady state forces and moments due to thrust. So if we have a symmetrical aircraft, then you're going to like this. The rolling moment due to thrust is 0. The side force is 0. And the yawing moment is 0 because it's symmetrical. If it's not symmetrical, then it gets really complicated. And instead of writing it all down, I'm going to show you what he shows in a figure in there. For each engine, you have to look at the direction of the thrust and all of the moment arms and calculate the net yawing or rolling or side force from those. Yeah. The screen what? Yeah, I should be sharing the screen here just a second. Let's see if this. You're getting that, right? Yeah. Except that's not the one I want, so hang on. There it is, okay. So if it's not symmetrical, then you have to go through all of this junk. So the thrust line here's the thrust vector here. And so you have to take components in the X, Y, and Z directions. And then you have to take all these moment arms and take the forces times the moment arms and get all kinds of formulas. And you look at the angle of the thrust. So here's why is it not highlighting anymore? Yeah, I'm still getting used to this. All right, so you have to take these angles of the thrust line, the phi sub t and the psi sub t, so that's the angle that it's canted up and outward, and then multiply by all the moment arms, and you get really complicated formulas that we're not going to go into, but you'll see them in the book, where if you do have engine, like a twin engine aircraft, and one of the engines goes out, then the thrust may not be symmetrical anymore, and you have to include all these effects. We'll simplify it later on when we look at the one engine in operative, and we'll just be given the yawing moment due to the thrust, and then we'll deal with it. And that's the picture that we saw when we did the longitudinal forces and moments, where we defined the different components of the thrust in the longitudinal plane. So that was easy, right? All right, so I am going to switch, and let's write on the board for a little bit just to change things up. We'll do that for the 10 minutes that we have left. So we're now done with chapter 3, the steady state forces and moments. We will come back to chapter 3 when we want to look at the perturbed forces and moments. So we're talking about perturbed flight, but we're not going to do that yet. So we're going to jump to chapter 4. And we're going to study steady state flight. Which is essentially trim conditions. And we're going to trim in cruise. So that's the normal thing that we did in 514. We'll also do a turn and a pull up. And we'll do both longitudinal and lateral directional trim. And then we'll do the one engine in operative case. So that's a twin engine aircraft. Where the right engine stops working and you get a big yawing moment when we do the thrust of the left engine. So we're going to hit this, and then we're going to come back to chapter 3 to do the perturbed forces and moments, and then we'll go to chapter 5 to do the dynamic analysis. Yeah. OEI, one engine inoperative. Thanks. Yeah, you would think one engine out, something like that, but it's one engine inoperative. Yeah, and thanks for watching the chat. All right, so along the way, we were going to look at what are called flying qualities. And in steady state flight, we're going to look at, well, do we have enough aileron or rudder or elevator to do what we're trying to do, to fly that condition? That's sufficient control power. Also, can we maneuver from one state to the other? Why is my computer beeping? Software change is required. We're not going to do that now. And then we don't spend much time on this, but the control forces have to be acceptable. That's an ergonomics or human factors issue. Can you hold the stick in the position it needs to be in? And then 4, we'll look at in chapter 6, what are the dynamics due to a disturbance? And the specifications that we'll look at, especially in chapter 6, come from the various regulations for flight. So these are called airworthiness requirements. And for the civil aviation, if you talk to any of the airplane people, you may have already heard these. You talk about FAR Part 23. These are the codes of federal aviation regulations. So this is Federal Aviation regulations. It's hard to write like that. So part 23 is for aircraft with a gross weight less than 12,500 pounds. And then if you do FAR part 25, it's heavier stuff. So less than 12,000 pounds, that would be like the personal aircraft, some of the lighter biz jets. This is commercial aircraft here. And then there is what's called the joint air regulations for very light aircraft. So if you have like a hang glider or a sailplane, some very light airplanes, there's a separate set of standards for those. And then the military has their own deal because combat has a lot more requirements than taking off, flying somewhere, and landing. And we mention those because a lot of times FAR Part 23 or 25 may not specify something, and people will use the military specs for that. And these are referenced in your book, or you can do a Google search and actually get these. These are military standards. You look at this and you go, wow, how many standards does the military have if this is 8,785C? They have standards for everything. And the way that we show that we satisfy either the FAR Part 23 or the mil specs, it's all done the same way, is you do preliminary design calculations, and then you build a wind tunnel model, because you can do that. And think about the Wright brothers, right? They tested their airfoils in a wind tunnel before they flew. So you preliminary design calculations, wind tunnel test. You do what we're doing in here. So we do equations of motion, both analytical and numerical. So you can do the calculations that we do in here. You can do numerical simulations, flight testing, not flight testing, flight simulation and simulation. And then the ultimate test, of course, is flight test. And you do these in this order because the preliminary design costs maybe $1. The wind tunnel test costs maybe $2. This stuff costs maybe $1 or $2, and the flight test can cost a lot of money, right? Especially if you build the airplane and you haven't done this stuff up here and it crashes, you lose your whole airplane. How are we doing on time? Time to quit. We'll start with static stability criteria, which we've already been talking about, but we'll formalize next time. You have to remember this because it's important. It's important. Yeah, remember I said the test ends with the longitudinal forces and moments. So last lecture, I think we wrapped that up where we defined the neutral point, aerodynamic center of the airplane. So once we started the lateral directional forces and moments, that's the cutoff for the test.